This lab is an introduction to the planets in the solar system. One of the most important things we're going to talk about is this table of planetary data. Now, I certainly don't want you to memorize this table, but I am going to walk you through it because I want you to be able to use it on tests, quizzes, and in lab, of course. So let's take a look at what's here. Basically, there's two parts to the table, the upper part and the lower part. So we're going to start on the upper part. Here we have the planets listed from closest to the sun to farthest from the sun. And then these are some symbols that people sometimes use for the planets. And then we have mean distance from the sun. And this is given in AU units, which if you forgot what that means, you just follow the asterisk. It means an astronomical unit, Earth's mean distance from the sun, or millions of miles or millions of kilometers. So you have three different ways of discussing the distance of the planet from the sun. Then we have the period of revolution. Revolution is an important term to differentiate from rotation in this class. In this class, revolution means orbiting another object. So this is the period of time it takes to orbit the sun once. And if you forget revolution and rotations down here and you confuse them, just look at Earth. So here's Earth, and its period of revolution is 365.25 days. So you probably could figure out, 365 days is how long it takes Earth to go around the sun. So that's revolution. The rest of these are listed also in Earth days and Earth years. Technically, it would take Mars, for example, 1 Martian year to orbit the sun. But we want to know in Earth years or Earth days. So here's Mars's period of revolution in Earth days. Next, we have the inclination of orbit. And what the inclination of orbit means is this. First of all, there's a flat plane called the ecliptic. And the sun is in the middle, and the Earth goes around the sun. And that plane that's defined by Earth's motion around the sun is called the ecliptic. It's an imaginary plane, but it is defined by Earth going around the sun. And astronomers have decided that that is essentially zero. And other planets are maybe not necessarily orbiting the sun in that exact same plane. They might be tilted a little bit more this way, or a little bit more this way, or a little bit more this way. And so that inclination means angle. How much are their orbits off from Earth's orbit? So here we are back at our chart. And so what this means here is Earth, you can see, is 0. And this is the angle at which those orbits vary from the Earth's orbital plane. So Mercury is off by about 7 degrees. Uranus is only off by about 46 minutes. Remember, that's a fraction of a degree. So that's what that column means. Then we have orbital velocity. Velocity is speed. How fast are these planets moving around the sun? And we have miles per second or kilometers per second. You can choose your favorite units. If you look at these numbers carefully, you'll see that the farther a planet is from the sun, the slower it travels. Interesting fact. All right, now we'll go to the second part of the table. And again, we have the planets listed here. So really, this is just a continuation of the table. So now we have period of rotation. So rotation is the spinning on an imaginary axis. So one spin on Earth is what we call 1 day, 1 24-hour time period. And all the other planets have their own time period of one rotation. And again, if you forget rotation, revolution, which is which, look at the Earth. The Earth is listed with 23 hours, 56 minutes, and 4 seconds because it's a little bit shy of 24 hours. And you'll remember, that's how long it takes for us to spin once on our axis. The others are listed in days and hours and minutes of Earth time. So Mercury takes 59 days to spin once on its axis. These gas giants, the Jovian planets, spin very, very quickly. In fact, Jupiter spins once about every 10 hours. And given the size of Jupiter, that is an amazing speed. Next, we have diameter. And we can have diameter in miles or kilometers. Remember, diameter is the entire distance across the planet. Radius would be half the diameter from the center of the planet to the surface. We then have the relative mass. Well, the masses of the planets are known, but they're really large numbers in kilograms, and they'd be kind of meaningless to us. So instead, we're just going to say Earth is one mass unit. And we're going to put all the other planets in terms of the Earth's mass. So for example, Jupiter is 317 times more massive than the Earth. Mars is about a tenth as massive as the Earth. Neptune is 17 times more massive than the Earth, etc. Density is important. Remember, density is how compact something is. It's different than mass. Mass is how much material is there. Density is how compact is that mass. And so you can see that the densities vary quite a bit. And remember that the density of water is 1 gram per cubic centimeter. So keep that in mind because there's a question in here about water's density and the planet's density. Polar flattening, I'm not going to ask you about, but it has to do with the fact that when planets spin, their poles flatten a little bit. Eccentricity, this is how elliptical is their orbit. Remember, the orbits of the planets are not circular. Kepler showed that they were elliptical. And eccentricity, as it describes down here, if you look at the dagger, is a measure of the amount an orbit deviates from a circular shape. The larger the number, the less circular an orbit. So a perfect circle would have an eccentricity of 0. And if you could make an ellipse with a pencil and 2 tacks, like I showed you in another video, and you stretch those tacks as far as you could with this string, and they made a straight line, that would have an eccentricity of 1. So everything is between 0 and 1. The closer it is to 0, the more it is a circle. So most of these are very, very close to being a circle, but they're off a little bit. Finally, the number of known satellites. This changes all the time as we find new moons around various planets. We call them satellites, but essentially that's the number of moons that are orbiting the planets. All right, so I took a lot of time to go through this because this lab is all about answering questions related to this table. So the first page is page 33, and the first activity you're going to do is activity 1. It asks you to briefly describe the nebula theory, describe the composition of the inner outer planets, and a couple other things related to how the planets formed. So I didn't put this particular page in my PowerPoint, but the page before it, page 32, describes that right here. This is the opening of the lab. This is right after the main page, so that you'll find the answers to that first activity right there. You're going to do all of the questions in activity 2 except question 3, which had to do with making a big timeline and showing the spacing of all the planets and all their sizes and stuff. So again, I guess you're lucky you don't have to do this activity. And question 3 has to do with table 2, so you don't have to do that either. Questions in activity 2, again, are asking about the table. For example, number 1 asks you to draw a line on this chart here between the terrestrial and Jovian planets and label it the asteroid belt. This question here asks you what's the largest terrestrial planet, what's its diameter. So you're just going to go along and answer the questions. On the next page, page 35, a lot of students have problem with that top question. How many times larger is the diameter of the smallest Jovian planet than the largest terrestrial planet? Well, you just figured out which was which in the previous question. And what you're going to do is you're going to take the diameter of the smallest Jovian planet that you determined, and you're going to divide it by the diameter of the largest terrestrial planet. And just make sure you use the same units. Use kilometers divided by kilometers or miles divided by miles, and you'll get how many times larger the smallest Jovian planet is compared to the largest terrestrial planet. The rest of these questions have to do with similar things of looking at sizes. Number 8, you're going to take the sun's diameter and divide it by the Earth's diameter or Jupiter's diameter. Activity 3 asks you about the inclinations of the orbits. And so what I showed you before with the notebook, that's what these questions are about. And you're going to look in that column for those answers. You're going to do activity 4A, B, and C. And these are all looking at the mass of the planets and thinking about the fact that the more massive something is, the more gravitational attraction it has, the more pull it has on other objects. And so these are some summary statements. Now for 4C, it asks you to use 2 different colored pencils. Please follow that direction, or pens, because students often don't. And you're going to put on the next page on a graph the diameter versus the density of each planet. So let me show you a little bit about how you're going to do it. Oh, and also it says label each point with the planet's name. So please make sure you do that. So this is the graph, and you're going to use information from this data table. You're going to use the diameter in kilometers and the average density as given here. So let's blow up this table and look a little more carefully at how to do this, because there's something a little bit tricky in the y-axis. So let's do Mercury. Mercury's diameter is 4,878 kilometers. That would plot somewhere along this line on the graph. Now you might be thinking, what 4,000? Well, these are all listed in units that are supposed to be multiplied by 1,000. So 40 really means 40,000 kilometers, and 110 really means 110,000 kilometers. So 5, which isn't written here, but would be halfway between 10 and 0, would mean 5,000 kilometers, and that's pretty close to what this is. So I just warn you about that, because that's the one thing about this graph that people find tricky. So Jupiter, for example, 143,000 is going to be up on this line here. Then we look at the density, 5.4, and we figure out where these 2 lines intersect, and we put a dot. So that's how you do this graph. And don't forget the name. The rest of these questions have to do with mass and density. Then you're going to do activities 5A and 5B, and these have to do with speed. Remember, speed is distance divided by time. And down here is a use of Kepler's law, my favorite law, as you know. And if you didn't look at the Kepler's law description on Canvas, you should do that. And then finally, I just assigned 3 summary questions at the end, and including another Kepler question. All right, so don't forget, come to my office hours for help if you need it.